Good morning, everyone, and thank you for attending this session. My name is Antonio Carrillo, and I am pleased to present our research titled Experimental Performance Characterization of a 30-60-degree box solar oven. This work has been developed in collaboration between the University of Málaga in Spain and the University of Algarve in Portugal. This slide shows the main features of the solar oven. In a 30-60-degree solar oven, we can set the collecting area at either 30 or 60 degrees above the horizontal. These two fixed inclinations let the oven naturally follow the seasonal variation in solar altitude. The vessel always remains perfectly horizontal, keeping liquids stable. The entire adjustment is made with one quick flip. There are no moving parts. Some construction details. This oven is hand-built by the Spanish artisan Narcís Puig from locally sourced materials. The window is made from simple 4 mm clear glass. When the flat reflector is in place, the effective aperture area is approximately 0.60 square meters. Inside, a 0.5 mm aluminum sheet painted in black is the absorber. Finally, it has around 2 cm of fiberglass wool insulation in all opaque envelope. Any cooking vessel that fits the available space can be used, provided it is suitable for oven cooking. In our experiments, we use black painted steel pots with 20 centimeters of the diameter and 10 centimeters height. It has a maximum volume of about 3 liters, but the typical useful volume when cooking is 2 liters. We carried out two types of tests, the water heating tests and the stagnation temperature tests. This slide describes the water heating tests. For this kind of test, we use the 2-liter water load and we place it inside the oven at ambient temperature, and then the oven is azimuthally tracked every 20 minutes. All these tests are conducted in a 4-hour window around solar noon, so the solar conditions are stable, more or less stable. Throughout the process of heating the water up to near boiling, we record all relevant environmental variables, solar radiation, ambient temperature, or wind speed, and so on. All these experiments were conducted in Málaga in Spain with 36.7 degrees north across different seasons, in winter, in equinox, and also in summer solstice, to assess, to know how the oven performs for different solar altitudes. This example in this slide presents the results from 3 tests conducted around the spring equinox of 2023. The solar altitude was about 53 degrees. In this particular test, the oven was in a 60 degrees position for high sun. Each point in this plot represents an experimental observation of heating power, calculated from the rise in water temperature in a 10-minute interval. This power is the y-axis. This heating power is plotted against the temperature difference between the water and the ambient. This is the x-axis. By applying a linear regression to the data, we identified this line, a relationship where the available heating power starts at 153 watts, and then there is a negative slope of 0.61 watts per degree of difference of temperature between the water and the ambient air. This slope, this number, represents the oven's overall heat loss coefficient. It represents how much useful power is lost as the water temperature rises relative to the ambient air. There is a reference point and special point here for a temperature difference of 50 degrees, and this is the useful heating power of about 122 watts. This is an average value representative of the heating performance of the oven in this process, in this boiling water process. In more practical terms, this oven can boil 2 liters of water in about 1.5 hours on a sunny day. In this slide, I will present how the oven performed in water heating tests across different seasons in Malaga. We made a lot of tests, and here you can see the heating observations of heating power that are grouped by solar altitude. We have the yellow points for 35 degrees, more or less the winter solstice. 55 degrees is in equinox, and then 65 and 75 degrees is in summer when the sun is high in Malaga. In these tests, where the oven was positioned in low sun position in 30 degrees. We have also the other group with the sun with the oven position in 60 degrees, but we are presenting as an example this one. Then, as the oven was positioned in 30 degrees, then it performs better in winter and less efficiently in summer, because there is some misalignment of the sun and the oven. The misalignment clearly reduces the heating power. For example, in winter we have 125, whereas in summer, in equinox, we have only 95 watts. If we focus in the summer solstice test, this one, 75 degrees, the purple points, we notice something interesting. Because the oven alignment is so poor and the sun, the test takes a lot of time and the sun drops very low, and then at the end of the test, the oven becomes better aligned, you see, and then the heating power increased again. And then the final data points in these areas, the heating power shift from the 75 degree group to the 65 degree group as the sun moves lower and lower. Stagnation temperature. These experiments were carried out in Malaga in different seasons and solar altitudes. We cover solar elevation angles starting in 20 up to 65 degrees. We have more tests to do here to be complete. Two ovens were placed side by side, one in 30, the other one in 60 degrees. This arrangement allowed us to clearly compare the performance of both configurations under identical conditions. We perform azimuthal sun tracking every 20 minutes. As the solar elevation changes slowly over time, the oven can reach near stagnation conditions. The internal temperature stabilizes close to its maximum for the given radiation. In this plot, we show in the y-axis, we show the stagnation temperature about the ambient temperature. And this data has been normalized, normalized to a reference irradiation of 1000 watts per square meters. So we can compare across different solar conditions. And here in the x-axis we have the solar altitude. We observed that the oven can reach maximum stagnation temperature over ambient of about 150 to 160 degrees with good radiation, and so this is a reference value for the maximum operating temperature that one can expect from this oven. This is useful for evaluating his potential cooking applications. And another important insight from these tests is that stagnation temperature changes a lot with solar elevation, with solar altitude. This is strongly connected to the oven's optical efficiency. With these curves, we can know which are the optimal solar elevation ranges for each tilt configuration. There is a crossing point here between the two positions around 50 degrees of solar altitude. For altitudes below, the good one is the 30 degrees position, and for higher solar elevation, this is a good configuration, the 60 degree position. These results suggest that if you change here, this oven with this design can perform very effective across a wide range of solar elevation angles, so we can get a consistent optical performance throughout the year and throughout the day as the sun position changes. Final conclusions. This is an ongoing work. We have already tested partial loads, the effect of partial loads, and also different pot lids. And we are planning to explore the effect of reflective oven walls, interior oven walls, also a thicker oven plate here, the horizontal plate, for a better heat conduction to the pot, and maybe redesign the optical external concentrator. Maybe we can get a better performance. Okay, that's all. We would like to hear from your comments and maybe work suggestions. Thank you very much for your attention.